In the previous video, I introduced the idea of stable and unstable equilibrium points. By considering several examples, we saw that feedback loops are related to the stability. In this video, we further investigate feedback strength to be able to better analyze the interplay of feedback loops and equilibria. As part of this work, I will introduce two new ideas, parameters and sensitivity. Let's start with parameters. A parameter in a stock flow model is a quantity that is not itself a stock or a flow in the model, but affects one or more flow rates in the model in some specific way. We've already considered stock flow models with parameters, but haven't yet discussed that piece of the models. Here I have the stock flow model for phosphorus. As mentioned before, inflow comes from two sources, pollution, largely from agriculture, and from plant and algae uptake of phosphorus from lakebed sediment. The plant and algae population is proportional to the amount of phosphorus already in the lake, and thus is controlled by the stock level. We can show this with a control arrow from the stock to the inflow. Pollution, though, is something that comes from outside the system, so it can be represented as a parameter. This is included in the yellow box. Note that the parameter increases the inflow of phosphorus into the lake, so we indicate this with the plus. Just as we measured the strength of control arrows, we can also measure the strength of parameters by checking how a change in the parameter affects the flow. In the case of pollution, each ton of phosphorus in runoff directly increases the inflow by 1 ton, so this parameter has a strength of +1. We can see what this means from a graphical perspective. On the graph, the outflow is represented by the blue line. Recall that the outflow is a constant 50% per year of the phosphorus present in the lake. We represented this by a strength of 0.5. I've included two different inflow plots representing different levels of incoming pollution. The green curve represents a pollution level of 15 tons per year, and the orange line represents a pollution level of 20 tons per year. Notice that these curves look very similar, but the orange curve is shifted up 5 units, corresponding to the 5 ton per year increase in the pollution level. This one-for-one relationship corresponds to the parameter having strength 1. Here's another example where a parameter helps us better model the situation. This is the stock flow system for the Naked Planet model, but I've now incorporated the greenhouse effect as a parameter. Notice that this parameter is shown as having a direct negative effect on the long-wave radiation, capturing the fact that the greenhouse effect prevents heat from escaping the planet. To model this parameter in an equation, I've incorporated it into the original description of outflow we obtained from Stefan's law. Using this formula, I plotted flows for this model for several different parameter values. The earth temperature is along the horizontal axis, and the flow, a measure of power, is along the vertical axis. The constant inflow from the sun is represented in green. The orange curve shows the inflow for G = 0. This corresponds to the original Naked Planet model with no atmosphere. We can see the equilibrium occurs at point A, giving an equilibrium temperature of about 255 Kelvin, or an average worldwide temperature of -1 degree Fahrenheit. The blue curve shows the inflow for G = 1. This corresponds to the glass ball model. The equilibrium occurs at point C, giving an equilibrium temperature of about 300 Kelvin, or an average worldwide temperature of 80 degrees Fahrenheit. The actual average temperature is about 60 degrees Fahrenheit, or 289 Kelvin. This corresponds to G = 0.65. This is the curve in magenta. In both of the previous examples, changes in parameter values led to changes in the equilibrium points. This motivates the notion of sensitivity. The formula for sensitivity computes the change in equilibrium value for a change in parameter value. Here, S1 and S0 represent two different equilibrium values for two different parameter values, P1 and P0. Let's return to the phosphorus example. Recall that the parameter here describes the inflow of phosphorus due to pollution. I've plotted the phosphorus inflows for two different levels of the parameter. Focus on the equilibrium point farthest to the right. When P equals 15 tons per year, I estimate that the equilibrium occurs at a stock level of 200 tons So we have P0 is equal to 15 and S0 is equal to 200. When P equals 20 tons per year, the equilibrium occurs at roughly 217 tons. So we get P1 is equal to 20 and S1 is equal to 217. Therefore, at this equilibrium point, the sensitivity is equal to 217 minus 200 over 20 minus 15. This comes out to be 3.4 years. To better understand this number, we can compare it to the sensitivity at the lowest equilibrium point. Here, the sensitivity turns out to be roughly 2.2 years. This lower sensitivity value at this equilibrium highlights that the equilibrium point will change less than the higher one for the same change in the parameter. Two more notes on sensitivity. In the previous example, we used stock values to estimate the sensitivity, but we can also use the sensitivity to predict a change in the stock level. Also, the sensitivity can be calculated as minus P over Q, where P is the parameter strength and Q is the overall feedback strength at the equilibrium point. I won't expect you to use this formula, but you may come across it in the textbook reading.